All right, welcome everybody. Thanks for tuning in. You are officially tuned into the Boise State Physics First Friday Astronomy event. My name is Brian Jackson. I'm a professor here in physics at Boise State. Teach physics and astronomy, lots of really great things. For those of you who have never joined us before, this is the First Friday Astronomy event. These take place on the first Friday of every month. So if it's a Friday night and it's the first one of the month, 7:30 Mountain Time, we're going to have a talk for you. We invite space scientists from a wide variety of fields. We're going to hear tonight about galaxy clusters, but we have planetary scientists. We have people who work on NASA missions. We've had space policy folks, people who work with the government, science writers. So First Friday Astronomy covers a really wide range of topics. But if it's the first Friday that's of the month, it's going to happen. So we have a really exciting lineup for you this coming season, this fall. And I just want to share that with you before we dive into tonight's very interesting talk. So here's our lineup for this coming fall. The fall season will start on September 3rd. And we're going to have Dr. Lori Fenton from the SETI Institute, the Search for Extraterrestrial Intelligence Institute. She is a planetary geomorphologist, and so she's going to tell us a little bit about her work studying how wind sculpts a planetary surface. Dr. Jim Ennis from the Fermilab is going to tell us a little bit about the Dark Energy Survey. This is a really exciting survey to learn more about dark energy throughout the universe, and I think we might hear a little more about dark energy tonight even. Dr. Joanna Teskey is at the Carnegie Earth and Planets Lab in Washington, D.C., and she's going to tell us about her work using the NASA James Webb Space Telescope, which is slated to launch this fall. Fingers crossed that actually happens. They have been delayed, but hopefully it'll happen. And Dr. Teskey will come in and tell us about her research on that. And then we're very excited to be able to welcome one of our Boise State alumni, Tyler Gordon, who's a senior graduate student at the University of Washington's astronomy department, who studies stars, exoplanets, and exomoons. And he'll speak to us in December. And so these events will for sure be live streamed. We're hoping that the COVID situation will cool down enough that we can host these events in person again. But whether or not they're in person, they're definitely going to be live streamed. So you're always able to watch the presentations at this link at the bottom. It's boi.st/astrobroncoslive. And for those of you who found it, this links you to the YouTube channel where the talks are live streamed and then also recorded. So if you want to see some of the previous talks, you can actually go to the same link and see the previous talks there. These events are entirely donation supported. It's folks like you who attend these that help to support these. And even if we have them virtually, they still cost. We send thank you gifts to our speakers as a way of thanking them for their presentations. And so if you're interested in helping to support this effort, go to give.boisestate.edu/astronomy, and that'll give you a chance to donate to help support these events. Okay, and with that, I'm very excited to welcome our speaker for tonight. This is someone many of you probably know already. Our esteemed colleague, Professor Heidi Wu, joined the physics department at Boise State just last year, and she has this really interesting and long academic pedigree. She got her PhD in the physics department at Stanford University, and then a bachelor's degree in physics from National Taiwan University before that. She served as a postdoctoral fellow at several institutions. She was a research fellow in the Department of Physics at the University of Michigan. She was a postdoc in the Department of Physics at Caltech. After that, she was at the Ohio State University in their Center for Cosmology and Astroparticle Physics. And so tonight she's going to tell us a little bit about her research in galaxy clusters. And with that, let's welcome Professor Heidi Wu.
Yeah, thank you so much, Brian. Share my screen. For the most of the human history, our view of the universe has been changing. About 100 years ago, we realized that our Milky Way galaxy is not the entire universe. There are other galaxies outside our Milky Way. Then we observed some galaxies live in groups. or they are crowded in a small region in the sky, and we call them galaxy clusters. Here is a picture of a galaxy cluster taken by the Hubble Space Telescope. For the past 100 years, astronomy is full of surprises. Astronomers have learned that the universe is expanding and it is actually accelerating. And there's this mysterious dark matter and dark energy. Tonight, I will share with you the journey how galaxy clusters played an important role in helping us making sense of the universe and shape our understanding of the universe. My title is Giants in the Universe, and this title is actually inspired by my colleague, Anja van der Linden, and also the fairy tale Jack and the Beanstalk. And I call them giants because they are really massive. They are about 100 to even 1,000 times more massive than our Milky Way galaxy. And I call them rich, invisible giants. So you can think of these galaxies as the gold coins or gold medals, if you will, of these giants. These giants are themselves are invisible, but we can look at these gold coins they carry. So we can see those gold coins, and then we can know where they are in the sky and infer how much mass there is in the sky. The earliest written record of galaxy clusters dates back to 1780s, or about 150 years ago. Back then, Charles Messier in France and William Herschel in England were hunting nebulae. So back then, nebulae basically refers to all these fuzzy objects in the sky that are not comets. So now we know that some of them are actually galaxies, but back then they all basically look the same. They are called nebulae. So Messier found that there's this crowd of nebulae in the constellation Virgo. And Herschel noticed that there's this, he called it concentration of nebulae, but another crowd of nebulae in the constellation Coma. And nowadays we call them Virgo Cluster and the Coma Cluster. They are basically the two galaxy clusters that are closest to us. But I'm ahead of myself. Back then, they didn't know what they are. So there's not very much development for about 100, 150 years because people really didn't know what nebulae were. So in 1920, there's now this famous great debate between Shapley and Curtis. This debate is basically about this object on the sky. We call it M31. We now call it Andromeda Galaxy, but back then it was called the Andromeda Nebula. So the question is basically, is this Andromeda Nebula part of the Milky Way galaxy, or is it actually outside our own galaxy or the system itself? So Shapley thought that this M31 is part of the Milky Way galaxy. But Curtis thought that this should be way outside our Milky Way. There's no definite answer from this debate. More evidence were needed. And a couple of years later, Edwin Hubble measured the distance of this of M31 very accurately. He used this technique called Cepheid variables, and then which can help us determine the distances very accurately. He found that M31 is about 2.5 million light years away from us. This is much bigger than our Milky Way. Our Milky Way is a couple thousand light years big. So this is basically saying our universe is much, much, much bigger than our own galaxy. So this debate or the settlement of this debate is basically how big is our universe? it turns out it's much bigger than we previously thought. So when we mention Hubble, we often think about Hubble's law or the expansion of the universe. Actually, there are a few unsung heroes behind the discovery of the expansion of the universe. So actually start with Vestal Slipher. So Slipher discovered that all galaxies exhibits redshift, or basically all galaxies are moving away from us. Why? Why do all galaxies are moving away from us? Then Hubble, as I mentioned, that he's very good at measuring distances very accurately. He found that farther galaxies are moving faster. Compare his distance measurement with Slipher's velocity measurement. And he realized that this relation, that the farther galaxies moving faster, is actually the property of an expanding universe. And Milton Hutchinson is one of the most important assistants of Hubble, did a lot of measurements. And Belgian physicist Georges Lemaitre and the Russian physicist Alexander Freeman independently developed the mathematical theory for an expanding universe. When we talk about the expansion of the universe, we often use an analogy of an expanding balloon, as I show here. As the universe expands, the distance between galaxies gets stretched, and it looks as if galaxies are moving away from each other. If two galaxies are farther apart, the space between them increases more, and it appears as if they are moving away faster from each other. I would also like to emphasize that the space is expanding, but galaxies themselves are not expanding. Galaxy clusters themselves are not expanding because they are held together by gravity. And also it's sometimes a little bit confusing, but the universe is expanding. It's not taking more space, because the universe is space itself. The space itself is expanding. So about the same time was the hint of dark matter in the universe. And it was developed by Swiss astronomer Fritz Zwicky. Back then was working at Caltech that time. So he measured the velocity of Coma cluster. So we know that just like the Earth orbits the sun, the sun is orbiting the Milky Way. Almost everything in the universe is orbiting something bigger. So it's the same as galaxies in clusters. So in this cartoon picture shows that the galaxies is in a cluster is orbiting the center of this cluster. So if the galaxy is moving faster, we know that this cluster is more massive. There's more mass in this cluster. So by measuring this velocity, Zwicky infer how much mass there is in this cluster. And he found that this mass is much bigger than what we infer from the visible mass. So there's this invisible mass that we just doesn't emit light, we cannot see, and he called it dark matter. But back then, the measurement was still quite uncertain, so this still remains a theory, not fully proven yet. So Zwicky actually came up with this idea, quite radical idea at that time. So he decided that there's so much mass in this galaxy cluster, it must cause this gravitational lensing effect. There's so much mass, it must bend light from a distant galaxy. Zwicky is way ahead of his time. So back then, the Einstein's general relativity was just developed, and the gravitational lensing of starlight by the sun was just observed, and then he proposed this phenomenon, and which was observed actually 60 years later in 1990s. Nowadays, this actually have become one of the most powerful cosmological tools we have, which I will come back in a little. So it's not until 1960s that Vera Rubin have provided very definite evidence of dark matter. So Vera Rubin was measuring the velocity of stars in a galaxy. So here, this graph, the x-axis shows the distance to the center of the galaxy. The y-axis shows the velocity of these stars. And these yellow points are observations from stars. Blue points are observations from hydrogen gas. And here, this dotted line is the theory, the theory prediction of the velocity derived from the visible matter. You can see this is way too low compared with observation. And this solid curve combines the mass of visible matter and dark matter, and it agrees much better with observation. And this has provided a very strong proof of dark matter. So dark matter was first theorized by Zwicky when he was observing Coma cluster, but Vera Rubin provided this very strong evidence for the existence of dark matter. So one very important milestone in the study of galaxy cluster was the first galaxy cluster catalog. It's called the Able Catalogue, first developed by George Able. He was using the Palomar Observatory in Southern California. And he used that observatory to scan it's actually a very big project, involves lots of people. And he basically systematically looked at the entire sky and search for galaxy clusters. This picture looks old school. Yes, it's taken from his original paper, 1958 paper. This is an image of a galaxy cluster taken using a photometric plate. So he documented about 3,000 clusters in this catalog. Of course, it's the telescope is at California, so it's Northern Hemisphere. And later on, Able's colleagues did a Southern Hemisphere survey and add the catalog, expanded the catalogs to about 4,000 clusters. So let me show you a few of my personal favorite Able clusters. This is called Able 2218. So this is a very spectacular gravitational lensing image. This is, of course, taken by Hubble Space Telescope. And you can see that these giant galaxy clusters, this giant got a really nice big gold medal in the center. And also you can see this big arc. This is the gravitational lensing. Basically light from galaxies that's far, far behind this cluster is distorted into this really magnificent arcs. And another of my personal favorite is this cluster, Able 1689. Unfortunately, they don't have fancy names, unlike galaxies. They are all known by their catalog number. And this is a very beautiful galaxy cluster with all these galaxies inside, and also very prominent gravitational lensing effect. So these two galaxy clusters are not only spectacular, visually beautiful, but they also have been really a treasure trove for the study of gravitational lensing. Astronomers have been learned so much about gravitational lensing, data analysis, dark matter structure using these two systems, among a few more others. So George Able defined, when he was making his catalog, defined this so-called richness of galaxy clusters. And it's basically the number of galaxies. So yeah, I think so I think of that, if the galaxies are the gold coins of the cluster, then you basically count how many gold coins to decide how rich this galaxy cluster is. So on the left side, this is a galaxy cluster. So you can see this. You can see that there are probably about 10 really big ones, probably around 20, 30 galaxies. And this is a relatively low richness cluster. And on the right-hand side, it's 1689 again. And then you can see there are several tens of really big ones. And if you count the smaller ones, probably it's close to a few hundred. So it's a high richness cluster. So this is not just for categorizing galaxy clusters. It turns out that the richness actually reflects how massive this system is. Of course, it's not. It's the richness. So richer clusters are like more massive than smaller clusters, and we will need gravitational lensing to further study their mass. So actually, you might ask, there are so many galaxies in this image. How do I know which one is associated with this cluster, or which one are just look as if they are close but actually very far behind or in the front? That's actually one of the biggest research questions I'm working on. This is actually one of the most difficult problems in the research of galaxy clusters. How do you know that these galaxies actually live in the cluster? So after looking at all these images of galaxy clusters, you might notice one thing. Almost all galaxies in clusters look orange, or we call them red galaxies. So in astronomy, we use the word red and blue kind of loosely. We call something red if it has more emission in red wavelength than blue wavelength. So it might actually look orange or yellowish, not necessarily red. And we call them blue if it has like more blue light than red light. So it might actually look green. So astronomers have been classifying galaxies. So this is the Hubble's galaxy classification scheme. So on the left side, we have elliptical galaxies. And it turns out elliptical galaxies tend to be red. And on the right-hand side, we have spiral galaxies, these with no bars and these with bars. And spiral galaxies are usually blue galaxies. Of course, there are always exceptions, but the exceptions are quite rare. Most of the elliptical galaxies in the universe are red, and most of the spirals are blue. Why is that? This is related to whether a galaxy is forming stars. So spiral galaxies, they are blue, and they tend to be forming stars. Elliptical galaxies, they are red. It's because they are not forming stars. So if a galaxy is forming star, it's making stars of all sizes, big and small. Big stars, they are usually blue and they are very, very, very bright, but they are also very short-lived. So these big, bright stars, they tend to burn out their fuels, burn out their gas very quickly. And on the other hand, small stars, they tend to be red, and they are fainter and they are long-lived. So if a galaxy is forming lots of stars, the blue stars will outshine all the stars, so they will look very blue. But if a galaxy does not form stars or has not been forming stars for some time, all the blue stars will die, like are all dead, and then now we can see the we can see the low mass red stars. That's why if a galaxy is not forming stars, it will look red. This is what's exactly going on in galaxy clusters. Most galaxies in galaxy clusters are red and ellipticals. They are not forming stars. Astronomers tend to call them red and dead. I don't like that phrase, dead in the sense that they are not forming stars. So why are galaxies in clusters not forming stars? This is actually one of the most important research questions we are trying to answer. There's no definite answer yet, but one of the possibility, or actually a quite popular solution or hypothesis, is that the supermassive black hole is blowing out a lot of the gas materials. Excuse me. So here on the right side is an image of a galaxy cluster, but it's actually taken at different telescopes. So there's this X-ray. Actually, I'll talk about that in a minute. Visible light and radio. Radio is basically imaging the gas that blow out by the gas blowout by the supermassive black hole in the center of this cluster. So we know that if we want to form stars, we need a reservoir of gas. But now there's this supermassive black hole. It wants to blow out things. And then galaxy clusters loses its gas reservoir. So then it's basically shut down its star formation because there's no material for forming stars. Again, this is still just one theory, but a very promising one. And then this is actually still a very, very active area for research. I was a little bit ahead of myself. I haven't told you that galaxy clusters emit X-ray. So in 1970s, and we start to have X-ray telescopes in space. We can't observe X-ray from the ground because the atmosphere shields us from all the X-ray from the space. So if we want to see X-ray from astronomical objects, we have to send the telescopes in space. The earliest X-ray telescopes are actually sent on these Aerobee rockets. So actually the pictures taken by X-ray telescope is not impressive at all. So you basically get one photon or two photons at a time. Yeah. So it's actually a very difficult measurement. So in 1970, NASA sent the first dedicated X-ray space telescope. It's called Uhuru Satellite. So Uhuru means freedom in Swahili, and this satellite was launched in Kenya. So they give it this name to thank the help of scientists in Kenya. So I mentioned earlier that galaxies in cluster move very, very fast. Actually, this is true for gas in clusters as well. But gas in clusters, they move very fast, but randomly, not orbiting around each other. We know that if gas is moving very fast, it means it has a very high temperature. So if a gas has higher temperature, it will emit wavelength. It will emit light with shorter wavelengths. So galaxy clusters is actually very, very hot. The temperature is about 10 million Kelvin or 10 million Fahrenheit. Actually, in that temperature, it doesn't matter which unit you use. It's very hot, and then with that hot temperature, it emits X-ray. This is you probably recognize the background is a combination of the optical image of this cluster I mentioned earlier, 1689, and then combined with this purple part is the X-ray observation taken by the Chandra Space Telescope. And I like to also mention this new X-ray telescope that was just launched 2 years ago by European Space Agency. It's called Erosita X-ray telescope. It is very special because this telescope is scanning the entire sky in X-ray. So, and then this hasn't been done for more than 20 years. Last time we did this was the Rosat Space Telescope, which finished in 1999. I'm very excited about the science that we will be able to learn from this Erosita X-ray telescope. And here is another very famous cluster. It's called the Bullet Cluster. The reason it's called the Bullet Cluster is because in X-ray, this cluster shows this shock wavefront, and it looks like the shock wavefront that the bullet passing some material. The bullet passing some material will also cause this shock wavefront. So what's special about this bullet cluster? This is actually two galaxy clusters passing through each other. So, okay, let me explain this first. So you can, the dark background sky and all these galaxies are optical images taken by the Hubble Space Telescope again. And this pink is the hot gas, the X-ray taken from X-ray telescopes. And this blue part are dark matter inferred from gravitational lensing. So when this, and then you can see there's this bigger cluster and the smaller cluster. And then basically these two galaxy clusters pass through each other. And then, so the smaller one was on the other side at an earlier time, and then they basically pass through each other. So the galaxies and dark matter are not disturbed, but the gas is actually disturbed and then causes this and this passing causes this shock wavefront. So this actually provides a very strong evidence of dark matter. Dark matter is not some gas that we haven't observed. It actually is its own. It's a type of particle on its own. It's not associated with the gas because we have seen a clear separation of this gas and the dark matter. So, so far we have seen that the development of cosmology and development of galaxy cluster studies are intertwined. So I like to mention this very important discovery of cosmic microwave background, or CMB, made in the 60s. So people have long predicted that the Big Bang theory has predicted that the early universe is very, very hot. And then as the universe expands, it cools down, the temperature gets lower. And so there should be some remnant of the heat of the Big Bang that we should be able to observe them. So it's long predicted. And Arnold Penzias and Robert Wilson were working at Bell Lab in the 60s, and they built a very accurate antenna with very little noise. And here, this picture shows the antenna they built. They weren't looking for cosmic microwave background. They just built this very awesome low noise antenna. And then they start to see there's this noise from everywhere in the sky. They cannot explain. And when cosmologists heard this, they knew they found the evidence or the echo of the Big Bang, basically. So what is cosmic microwave background? You can think of it basically as photons everywhere in our universe. It has this temperature of 3 Kelvin or minus 454 Fahrenheit. It is almost uniform. And you might have seen this picture from the Planck satellite. So it's very small fluctuation, but this fluctuation actually encodes lots of cosmological information. So how does it relate to galaxy clusters? It turns out I mentioned that there's this very hot gas in galaxy clusters. They can basically heat up these CMB photons. So here, for example, there's this CMB photons, 3 Kelvin, very cold. And then when they meet this hot gas of galaxy clusters, they will actually be heated and its wavelength will be changed. So this was first developed in theory by Sunev and Zeldovich, two Russian astrophysicists, or it's called SZ effect in short. And this is the SZ effect map or map of CMB and of the Coma cluster. So what is this SZ effect good for? Actually, it has helped us finding very, very far away galaxies. Sorry, very, very far away galaxy clusters. So here I'm showing this actually pretty famous cluster. It's called El Gordo. So El Gordo means the big fat one in Spanish. So this cluster was discovered using a CMB telescope in Chile. So they named it in Spanish. This galaxy cluster is very, very far away, 7 billion light years away. So, and this is actually one of the most, actually, I think the most massive galaxy clusters known. It's 3 times, actually, it's 3 million billion solar mass. So basically 3 followed by 15 zeros. I don't know if there's a name for this big number. So, or 3, yeah, so 3 followed. So, well, I think the problem is that the mass of the sun is so inconvenient for cosmologists. So, well, this galaxy cluster, they are so far means that it has formed when the universe was so young. So this actually generates a lot of interest, and actually people have been thinking, how is it possible that such a big cluster can form so early on in the universe? Is there some problem in our understanding of how galaxy clusters form, or is there anything wrong with our cosmological models, or even is there anything wrong with Einstein's general relativity that actually always sell magazines? I heard. So yeah, so people have been doing a lot of research and lots of simulations studying this El Gordo cluster. And it's only with this SZ effect I mentioned that we are able to find galaxy clusters that are this far away. So before I move on, let me quickly summarize what is in a galaxy cluster. And obviously it has galaxies, and Messier and Herschel have seen them. And I mentioned that the galaxies in clusters, they are usually red and elliptical. They are not forming stars, possibly due to the supermassive black hole inside. But it's the most spectacular part, but it's only 2% of the total mass of this galaxy cluster. And it has hot gas, and the gas is so hot it emits X-ray, about 10 million Kelvin. And then it also interacts with CMB photons in this SZ effect I mentioned. It's about 10% of the total mass. And finally, there's this big component that we cannot see. It's a dark matter component. It's about 88% of the total mass. We can't see them, so this is actually a computer simulation of the distribution of dark matter in a galaxy cluster. So my research actually used lots of simulations like this to help me better understand how galaxy cluster forms and how their gravitational lensing signal look. So I like to for the last part, I like to talk about basically dark energy and how galaxy clusters can help us understand it. So I'm borrowing this catchphrase from my colleague Dragon Hooter. The universe is caught speeding. So in 1998, Saul Perlmutter, Brent Schmidt, and Adam Rees led 2 teams of astronomers to observe this so-called Type 1a supernovae in galaxies. So what they were trying to do is to basically measure distances to galaxies at different cosmic time. So they can decide the expansion rate, acceleration or deceleration rate very accurately. So Type 1a supernovae are called standard candles in the sense that their luminosities are all the same for this kind of systems. So imagine you have a box of candles, all of them are equally bright. So if you put them at different distances, so if it appears faint, you know that this candle is farther away from you. You can look at how faint they are. You can decide how far away this galaxy or this candle is away from us. So using this technique, they were able to determine distances very accurately. And then what they found is a big surprise. The universe is not slowing down, it's speeding up. So since the discovery of the expansion of the universe, people have been thinking, is the expansion decelerating? Is it shrinking? Or is it decelerating and become a constant velocity? Or is it does it stop but not shrinking? Or is it coasting or moving at the same velocity forever? And the results from 1998 actually surprises everybody. It shows that the universe is actually accelerating. And this is very counterintuitive because we know there's dark matter. It provides gravity. Gravity pulls things together. So we were kind of expecting a decelerating universe. But it turns out the universe is accelerating. Why is it? We still don't know yet, but we gave it a name. It's called dark energy. So combine the discovery of acceleration of the universe, we now have this picture of what the universe is made of. So we know that energy and mass are equivalent, so we can kind of compare the mass and density, mass and the energy budget in the universe together. So approximately 68% of the energy density is in the form of dark energy. It accelerates the expansion of the universe. And about 27% is in the form of dark matter that we have been talking about, what Zwicky and Ruben discovered. Finally, less than 5% of the total mass is in the form that we are familiar with, gas and galaxies. So as a cosmologist, my job is to look for gas and galaxies in the universe and infer how much dark matter there is and where they are, and looking at dark matter at different cosmic time to infer how much dark energy there is. So I mentioned that dark energy slows down dark energy accelerates the expansion. It has another very important effect, that is, it slows down the formation of galaxy clusters. Here I'm showing two sets of simulations. This is basically simulating the density in the universe. The top one simulates the effect of dark energy. The bottom one shows the effect of no dark energy. So you can see these big bright clumps are the location of galaxy clusters. So you can see with dark energy, there's very little evolution at very different time. You can pretty much see the same structure at different time. But if the universe has no dark energy, there's nothing to slow down the formation of clusters. So you can see that the galaxy clusters actually grow very fast. They are formed very fast in such a universe. So by looking at galaxy clusters at different cosmic time, we can decide how much dark energy there actually is in our universe. This is actually my research is about. We look at a large area in the sky. For example, here is an image of a sky area, and then we look for galaxy clusters. And we, simply speaking, we basically make a histogram of their mass, basically in how many clusters there are versus mass. And from theory, for theory of a given dark energy, we can predict how many there are. In a universe with more dark energy, we expect to see fewer galaxy clusters and also slower evolution. Remember the images we showed earlier. In a universe with little or no dark energy, we expect to see lots of galaxy clusters and also a very rapid evolution. How do we measure galaxy cluster mass? Actually, this is my entire research field, but I will just mention that it's actually basically what Zwicky theorized more than 90 years ago, this gravitational lensing effect. And so I'm very excited about this. We now have this I'm very excited about this new survey mission. It is the Vera Rubin Observatory. This is a new telescope. It's just being built, almost done in Chile, and it will start observing next year. And it will spend 10 years scanning the southern hemisphere, half of the entire sky. And then take very accurate, very exquisite images of and providing us great opportunities to measure gravitational lensing effect. And of course, it's named after Vera Rubin, who provided evidence of dark matter. I'm also very excited and to be involved in this Nancy Grace Roman Space Telescope. So this is going to be launched in 2025, a NASA Space Telescope. And for a while, it was called WFIRST, Wide Field Infrared Survey Telescope. It has this name, wide field, because you want to scan a large area in the sky and you want a wide field instrument. And who is Nancy Grace Roman? She was the creator of NASA's space astronomy program. So NASA does not always focus on astronomy. So, but she basically pushes or developed the space astronomy program in NASA using space telescopes to do astronomy. And she led the planning of the Hubble Space Telescope. So she's often called the mother of Hubble. And I mentioned that this telescope is wide field. What does that mean? So here is like an edge of, excuse me, the Andromeda Galaxy. You can see that in the Andromeda Galaxy is much bigger because it's like a third of this Andromeda Galaxy. So if we take a picture using Hubble Space Telescope, the area will look like this. And similarly, if we take a picture with JWST, well, later this year, it will be about the same size. But WFIRST will have this really big area. So this is like we often say that one picture of WFIRST is like, or one picture of Roman Space Telescope is like 100 times the one picture of Hubble Space Telescope. The same image quality and then 100 times bigger. So we will have a lot of spectacular observation with Roman. So you might ask, haven't we figured everything out? Dark matter, dark energy, galaxies? The answer is actually no. So I call this the great debates of 2020s. Well, it's not official, I call it this way, but it will probably be called something else in history. But it turns out that cosmology is in a kind of weird, uncomfortable, or slightly embarrassing situation. We don't know how fast is our universe. We don't know how fast our universe is expanding. So if you are interested, you can look up this, we call it Hubble constant tension or H0 tension. So the problem is that, so there are several different ways to measure Hubble constant. You can use CMB. This is a map of the Planck satellite taken by Planck satellite. You can measure Hubble constant using that way and get a value. And then you can also measure Hubble constant using supernovae and get a different value. So it turns out there are two big camps of people. People who use CMB get a value about 67 plus minus 1 or 0.5, I forgot. And people use supernovae get a value of 73 plus or minus 0.5. So they are actually in total discrepancy with each other. So we don't know why. Why are these two different methods? They are supposedly both very accurate. Why do they give us so different answer? We don't know yet. This is still a lot of people and myself have been thinking and working on this. And that is just one of the debates. The other two is about how clumpy our universe is, and it's technically it's called SA tension. So SA tension, or sometimes sigma 8, this is a parameter describing how clumpy our universe is. So for example, if the universe is totally smooth, obviously it's not, but if the universe is totally smooth, then SA will be 0. And if a universe has like really big clusters and really big empty regions, then the SA value will be bigger. It turns out that CMB measured a SA value, and gravitational lensing provides another SA value, and they are different. And this is, we still don't know why yet. But hopefully this Vera Rubin Observatory and the Nancy Grace Roman Space Telescope will give us more data to help us understand this SA tension as well as the Hubble constant tension, as I mentioned. So in this talk, I have taken you through the journey not only about the cosmology development in the past 100 years, but also the development of galaxy cluster studies. And about 100 years ago, that we realized that our universe is not our own Milky Way galaxy. There are other galaxies, like Andromeda galaxies. And we start to observe galaxy clusters and then realize that there's actually invisible matter in these galaxy clusters. And then there's study using X-ray space telescope to look at the hot gas component in cluster. And finally, we also have been studying dark matter, their dark matter components using simulations. And using supernova, we found that the universe is accelerating. And now we have this really strange universe with lots of dark energy. And we like to study dark energy, like pin down the detail of dark energy using galaxy clusters, because the number of galaxy clusters in the universe is sensitive to how much dark energy there is. And to find to study galaxy cluster mass, we use this phenomenon called gravitational lensing. And finally, we have very exciting upcoming experiments, Vera Rubin Observatory and the Nancy Grace Roman Space Telescope, to help us better understand dark energy. Thank you.
That was excellent. Thank you so much. I have to ask you this question. Okay, I'm gonna use my chair's prerogative to ask questions.
Absolutely.
My daughter was explaining to me yesterday that dark matter is ghosts. I'm pretty sure it's not ghosts. So, but could you tell me what it is?
Dark. So that is, well, I think I've said this a number of times. It's some particles that we haven't discovered. It is not any of the particles that's on our periodic table or in the standard model of particle physics. So I guess all I can tell you is what it is not. So I can't really tell you what it is because this is still like a really active area of research. So I don't know if I will live to see that it's answered. I hope I can. So yeah, so it's why is dark matter not ghost? I think we can feel ghost, right? Yeah, but we can't feel dark matter, so dark matter must not be ghosts.
So how do you think we're going to figure out what dark matter is made out of?
Yeah, so there are several different. Actually, I didn't mention that in this talk. Maybe next talk. So there are several ways. We think there are several theories theorizing like what kind of particle that dark matter is. So to test these theories, there are both observations looking at, say, gamma ray in the sky, because some of the theories some of the theories predicts that dark matter can annihilate or interact with each other and produce gamma ray in sky. So people have been using gamma ray observatories to look for them, and people are also building very exquisite experiments like deep underground looking for the evidence of dark matter, because dark matter, although they don't emit light, but they do have gravity. So if we have very accurate or very low noise experiment, we can actually detect the gravitational or interaction between dark matter and some normal matter. So, okay, sorry, I was wrong. I said we can't feel dark matter. We can't feel dark matter on the Earth. So you see, obviously galaxy clusters, they do feel dark matter. So
Yeah, that's what I told her. I said we can't feel ghosts, and I don't think ghosts have gravity, but dark matter.
oh yeah, okay, yeah, that's
Do you want to?
a
I have
answer.
a question here that you partially answered, but maybe do you want to talk a little bit about dark energy as well? Do we have a sense for what dark energy is, where it's coming from?
So not really, actually. So all we have is, so it's actually, it's one of the biggest, or also one of the biggest puzzles. So we know it has to accelerate the universe, like what we observe, and but we don't know. So although I wrote 68 here, it's actually still quite uncertain. That's why we do the research we do. So, and it's uncertain, it's how much density there is. It's uncertain whether it depends, whether it evolves with time or not. Maybe there might be more dark energy. Maybe its property in the past might be slightly different from now. And yeah, so these are the properties we are trying to measure using galaxy clusters and other cosmological tools. So yeah, again, I don't have an answer for that. So I don't have an answer for that. It's still a research topic. I hope I will see it answered in my lifetime.
Yeah, it's so puzzling. Okay, we have another question here. You said, let's see, as you said, galaxies farther away from us are moving faster. Would this velocity play any role in your consideration when looking at gravitational lensing to determine cluster mass? Yeah, do you have to think about cosmological expansion when you're making these sort of mass measurements?
Yeah, absolutely. So we actually, so thanks to Lemaitre and Freeman, they have worked out all the math. So thanks to them, actually, the mathematics that describes the movement or the moving away of galaxies, there's a very good and accurate, I should say, a complete model for it. So yeah, using this model, this Lemaitre and Freeman's model, then, and so the entire gravitational lensing, the mathematics is built upon Lemaitre and Freeman's models. So then, yeah, then that's basically takes into account the expansion of the universe. It's a great question. I never get a chance to talk about the equations I use. This is really great.
And maybe we should have a very math intensive First Friday Astronomy sometime.
Okay, well, sign me up.
So here's a question for you. I see actually speculated about a lot. How do we know that there is dark matter and dark energy? How do we know that instead it's not just gravity just works differently at different scales in the universe?
Yeah, people talk about a lot. So there are several different ways. One, there are several different strong evidence. So this bullet cluster is actually one of the most strong evidence. So you can see that. So dark matter basically behaves differently than this gas. It just can't be explained by the so-called Maunder or modification of Newtonian gravity. And there's a very important but very super technical evidence that I only tell physicists, but I can tell Brian. So yeah, it's probably a little bit too technical for our audience. Is this thing called power spectrum of both CMB and the matter. So let's see, how do I describe it? So in the early universe, there's the very, very early universe is a bunch of plasma, basically photons and electrons, they are all mixed up. And there's this oscillation going on in this plasma. And then dark matter provides like a force to slow down or damp down this oscillation. So by looking at how damped down this oscillation is, we can determine how how much dark matter there is. So if there's no dark matter, this oscillation will be much crazier than what we see on this picture. But this picture, this amount of oscillation or fluctuation is consistent with a large fraction of dark matter in the universe. I don't know if that's understand.
You're talking about, this is the acoustic baryon oscillations?
Yes, exactly.
Okay.
That's
so these
exactly
little bubbles, the little tiny specks that are sort of the structure in this image, those are the sizes of these bubbles of plasma that you were describing, right? That's what you're saying?
Yes, roughly. Yes.
Those are the little bubbles of plasma. And so by measuring the sizes of those bubbles, as in this picture, we can estimate how much dark matter was involved with that oscillation. Is that what you're saying?
It's not exactly the size of a bubble, but the structure, because they are kind of big and small sizes, it's kind of looking at sizes of bubbles at all scales.
So basically, how many big bubbles relative to how many small bubbles, that tells you how much dark matter there was.
Yeah. So yeah, and that in Fourier space, that's called power spectrum, basically. Yeah, but that's a good way to explain it.
I don't know. It's not something I completely understood. So yeah, okay, that's good. That's good.
Yeah.
Good
So if there's no dark matter, this fluctuation wouldn't look like this. They will look much crazier, or completely different. I should. Yeah.
Yeah, that's really fascinating. Well, that was great. Well, thanks so much. I'm gonna grab the screen again if you don't mind. And so thanks so much for joining us, everybody. As I said, we're going to have the next one of these will be on, let's see, I'm trying to put myself in here. The next one of these will be on September 3rd, 7:30. We'll have Dr. Lori Fenton from SETI come and talk to us about her research on planetary geomorphology. It's going to be a really great talk. Please join us and have a great weekend, everybody.